So to save time, I wrote some definitions that I'm not sure you covered these definitions in the class or not, but they are very important definitions, and you will see these expressions a lot in the future courses. So it's not bad to see what they are. So do you know what is a convex set or convex function? Have you got familiar with them in other courses? Convexity? No? So let's see the definition. A convex set is a set that the convex combination of all the points inside that set is going to be again inside the set. What is a convex combination? It's the line segments between the 2 points is called the convex combination of those 2 points. Okay? So when you can find 2 points in a set that some of the line segments is outside of the set, that set is not convex. So for example, in this figure, the above figure, it's convex because whatever 2 points x and y you find, the line segments between them is inside that set. But in the below figure, you see for those 2 points, some of the line segments is outside of the figure, outside of the set. So the second one is not convex. So you can easily, if you see a two-dimensional set in x, y axes, you can easily distinguish, is it convex or not? But how mathematically we can write it down? First of all, how to write a convex combination of 2 points? It should be exactly between them. It shouldn't be like the line crossing them after x or a line crossing them after y. It should be between x and y. That's why, in order to specify the line segment between 2 points, I say, as you see, I define them as z. Lambda x plus 1 minus lambda y when lambda is between 0 and 1. If lambda is 0, it's point y. If lambda is 1, it's point x. And when lambda is between 0 and 1, it's on the line segment of x and y. For example, if lambda is 0.5, it's exactly in the middle. So the mathematical definition of a convex set is that for all x and y in S, let's say that the name of our set is S, for all x and y in S, convex combination of x and y should be inside S, meaning that lambda x plus 1 minus lambda y should be inside S for all lambda between 0 and 1. This has the same meaning as the one that I explained in the figure. All the points inside the set, the line segment between them, between any pair of them, should be inside the set. So you will see this definition of convexity a lot. And it's very important. But convex set and convex functions are two different things, related, but two different definitions. The convex function, hopefully you saw convex function before. For example, we say that y equal to x squared is a convex function. Convex functions they're looking up from the shape of it. You can understand that it's convex if they're looking up. As you see, it's like very, very similar to x squared. But how to emphasize it or state it in mathematical way? We say that the function of the line segment between x and y, we specify it with z, for example. As you see, it's here. This is the function at the convex combination. It should be less than or equal to, as you see, it's below the point above it. It's less than or equal to the convex combination of function at x and y. So whenever f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y, we say that the function is convex. It has the same meaning as the shape of the function is looking up. Two simple definitions. It's not hard to memorize them, but easy to understand. So knowing this, we have question 16 in the study set. And here we need to see that if that statement is correct or not. So I hope you have seen it in the previous math courses. When the question is stating that prove or disprove, if it's true, you need to prove it. If it's not true, you need to give counterexample. You don't need to prove that mathematically prove that it's not true. You just need to say that this is not true for this specific point. And when it's not true for one point, that's enough. It means that it's not true in general. Okay? So if you want to prove it, if you want to say that it's true, prove it. If you want to say that it's false, just provide a counterexample. Now, in part A, it's written that set S all x's that f of x is less than or equal to 10 is a convex set. And this is happening where f is convex and continuous function. Is it true or not? This is true, but how to show it? I want to show that set S is convex, right? Let me show it, solve it together for the first part. I want to show that S is convex. In order to show that S is convex, I need to show that for all x and y in S, required to prove lambda x plus 1 minus lambda y is still in S. If I can show this, it means that S is convex, as the definition states. So let's see if I can start from the left-hand side and conclude the right-hand side. If I'm talking about x and y in S, what was the definition of S? All the points that their function, their value of f is less than or equal to 10. So when x and y is inside S, meaning that f of x is less than or equal to 10, f of y is less than or equal to 10. If I multiply lambda, because I want to find something like that. If I multiply lambda with f of x and multiply 1 minus lambda with f of y, since lambda and 1 minus lambda are positive numbers, I would have lambda f of x less than or equal to 10 lambda, 1 minus lambda f of y less than or equal to 10, 1 minus lambda. And if I sum them up, I would have lambda f of x plus 1 minus lambda f of y less than or equal to 10 plus 10 lambda minus 10 lambda, which is 10. So I don't have the right-hand side yet. Now I will use the statements that the f is convex as well. So since f is convex, as I showed you in the definition of a convex function, f of lambda x plus 1 minus lambda y is less than or equal to this one as well. So I have some expression here. F of lambda x plus 1 minus lambda y is less than or equal to that expression, and it is less than or equal to 10. Now, now that I know f lambda x plus 1 minus lambda y is less than or equal to 10, so f of something is less than or equal to 10. This is the definition of a state S, set S. Whatever f of it is less than or equal to 10, that point exists in S. This is the definition of S. So from here, I can conclude that lambda x plus 1 minus lambda y is inside S. And I have the right-hand side in the top, which means that S is convex. So in the exam, if it's asking show something is convex, you need to go through this procedure. You need to start from two arbitrary points in the set and show that the convex combination of that point for all lambdas between 0 and 1 is still in the set. Is there any part of this proof you couldn't follow? We can discuss this if you want. Is it clear?
Last part, I couldn't get it.
The last part. So you understood that we have this part, right? So I know that the convex function, if f is a convex function, f of lambda x plus 1 minus lambda y is less than or equal to that expression that I've written here. So I can say that when this is less than or equal to 10, f of lambda x plus 1 minus lambda y is less than or equal to 10. This you understood, right? So what was the definition of S? The definition of S is whatever point x for which f of x is less than or equal to 10. So now that I showed for this specific point, f is less than or equal to 10. So this specific point exists in S. So I showed that the convex combination of x and y for lambdas between 0 and 1 exists in S, so S is convex. This is so we used like definition of a convex set and definition of a convex function. Let's see how is the part B. In part B, we have S for all x's in Rn such that ax less than or equal to b is a convex set where A is m by n and b is m by 1. I think this set is familiar because in the constraint of linear programming, we always are dealing with these type of constraints. Some coefficients multiplied by some variables is less than or equal to the right-hand side. So we want to say that this is convex. This statement is still true. Again, we start from two arbitrary points in S, and we want to show that its convex combination is inside S. So we can name the convex combination as Z. Z is equal to lambda x plus 1 minus lambda y for lambda between 0 and 1. And since x and y is a member of S, we can say ax is less than or equal to b. And ay is less than or equal to b, because this is the definition of set S. Again, I do the same trick. As you see, when you solve some problems, it becomes familiar. All the solutions are following the same steps. I multiply lambda with the first one, and I multiply 1 minus lambda with the second one. As you see, lambda ax less than or equal to lambda b, and 1 minus lambda ay is less than or equal to 1 minus lambda b. I sum it up. When I sum them up, I would have lambda ax plus 1 minus lambda ay less than or equal to lambda b plus 1 minus lambda b, which is actually b, because this is lambda b plus b minus lambda b. And as you see, I can factor a from this expression. So it is equal to a multiplied by lambda x plus 1 minus lambda b less than or equal to b. So I found a point that a multiplied by that point is less than or equal to b. So that point exists in set S. Since that point exists in set S, means the convex combination of x and y exists in S, so S is convex. That's the same logic. We're just repeating the same logic for different problems. If it's not clear, please stop me. I'm just going further, but I want you to understand what's going on. Part C, it's saying that S, with the same definition of the previous question, always has at least one extreme point. So for example, imagine we are dealing, if it's two-dimensional, we are dealing with like we call them polyhedrons, which is a convex set. These polyhedrons has some extreme points. So the question is saying that all the possible ax less than or equal to b's at least has one extreme point. So this is not true in general, because if it's empty set, if the intersection between the constraints, are empty, like this example, there is no extreme point because it's an empty set. There is no set involved. So what is this? It is like, assume that x1 even doesn't exist. x2 minus x2 less than, so x2 is bigger than or equal to minus 2. I think it should be exactly opposite, like this one. I will fix it. So here, for example, as you see, there is no common area when I'm dealing with this region and this region. So when there is no common area, their intersection is empty. And when their intersection is empty, there is no extreme point involved. So when they say that always has at least one extreme point, it's a false statement. Let's go to part D. S for all x's for which absolute value of x is bigger than or equal to 4 is convex. Let's see what is this x. So I have, let's say 4 here minus 4 here. I have this area and this area. Is this a convex set or not? Why not? So for convex set, we are not talking about intersections. So for linear programming, when we put all the constraints, this and this and this and this, we are talking about the intersection of all the points that satisfies all the constraints. But I'm talking about the set, I'm not talking about the intersection. If this set, this specific set, convex or not? Remember, the definition of convex set is that all the convex combination of them should be inside the set. Is it? Can you give me a counterexample? What point is not inside? Which is the convex combination of them? Just one counterexample. This is the only thing you need to write in the exam. Minus? Minus 5 to 0. Exactly. Practically minus 5 to 0 because we need just 1 point. You're giving an interval. Just 1 point. Whatever point you say between minus 4 and 4 is not inside the set, and it's a convex combination of them. For example, if I say minus 5 and 5 as two separate points, and if I say that lambda is 1 over 2, because lambda should be between 0 and 1, what is the convex combination of these 2 points? Minus 5 multiplied by 1 over 2 plus 5 multiplied by 1 over 2 is equal to 0. So 0 is a convex combination of 2 points in this set, but 0 is not in the set. So it's not a convex set. How did I write which one? This minus 5. So as you remember, we had lambda x plus 1 minus lambda y should be inside S for all x and y in S and for all lambda between 0 and 1. If I can find the points x and y inside S, and if I can find the lambda between 0 and 1, that this is not inside, that the convex combination is not inside S, that S is not convex. I just want the counterexample. I said, let's say x is minus 5 and y is plus 5. Both of them are inside S because their absolute value is bigger than or equal to 4. But when I put them inside this expression, lambda x plus 1 minus lambda y, for a specific lambda, let's say 1 over 2, which is a regular lambda that we usually define, I found point 0, and point 0, the absolute value of point 0 is not bigger than or equal to 4. So it's not inside S. So I found a point that I found x and y, that their convex combination is not inside S. So S is not convex. I hope it's clear. If you saw this in 2 dimensions, it would be more clear for you maybe. If you just, for example, say that this is 4, this is minus 4. Whatever point I select here and here, the line segments is not, some part of the line segments is not inside the set. So the set is not convex. That was the definition of a convex set that I already showed. So the last part, part E, is saying that consider two convex sets S1 and S2. Their intersection is convex or not. So actually this is all again happening in linear programming. Whatever constraint we write, we say this constraint and this constraint and this constraint. These ands are practically intersection, because the point that holds should hold in all of them. So if each one of them is a convex set, we are dealing with intersection of convex sets. And we know that the intersection of convex sets is also convex. So this question is referring to that part. I want to show that if S1 and S2 are convex, their intersection should be convex as well. Again, let me solve it again together, because I think it's more clear. The procedure is the same. If I want to show that a point is convex, a set is convex, I start taking two arbitrary points from that set. I want to say that S1 intersection S2 is convex, so I take two arbitrary points from this set. And I need to show that it's required to prove that lambda x plus 1 minus lambda y is in S1 intersection S2. If I show this, it means that for lambda between 0 and 1. If I show this, it means that S1 intersection S2 is convex. So when I say x is inside S1 intersection S2, related to the mathematics, I know that it means x is in S1 and x is in S2. So I can say the same thing for y. Let's add y here. So when x and y is in S1, and I know that S1 is convex, so I can write lambda x plus 1 minus lambda y is in S1. Again, I can write the same thing for S2. So some point is in S1 and that point is in S2. So that specific point is in the intersection of S1 and S2. So I can say lambda x plus 1 minus lambda y is inside S1 intersection S2, which is the thing that I wanted. It means that this point is in, the convex combination of x and y is in the S1 intersection S2, which I wanted to prove from the beginning. So the same procedure you need to follow. Take two arbitrary points from the set and show that their convex combination is inside that set. Let's go to the next question. First, let me jump to last question because I'm afraid I wouldn't have time to cover 17. Let's cover 18 first. In question 18, we have two linear programming problems, LP1, LP2. They have the same constraints. Let me show you this. So they have the same constraints, the same objective function. The only difference is LP1 is minimization and LP2 is maximization. No other differences. So part A is asking us to find the optimal solution of LP1 when the objective function is 4x1 minus 2x2. So you have seen it in the class, how to find optimal solutions for two-dimensional problem using the figure. So this is our figure. First of all, you need to be able to draw all the constraints. When you draw it, you see that the polyhedron, the feasible solution, is the figure that is being shown as a shaded part. So when this is the feasible solution, to find the optimal solutions, I only need to see to which direction I get minimum value. I go lower and find lower and lower values. First of all, regarding linear programming, we know that the optimal value happens at no. In linear programming, we know that the optimal values happens. I'm not hearing you. I can. More than? Corner points, extreme points. So we know that the optimal value should happen at the corner points. So without seeing the objective function, I know that these corner points, where they call it extreme points, can be the optimal solutions. But which of them is the optimal solution? It relates to the vector of objective function. So in the objective function, I have 4x1 minus 2x2. It means that I need to go and find vector 4 minus 2. And I know that with respect to this vector, if I go further and further, I would increase the value of objective function. So let's find 4 minus 2. As you see in the figure, I already shown it. 4 minus 2 is this one. This is vector of 4 minus 2. So with respect to this direction, the objective function value would increase, meaning that when I go to the right side, I would get more and more values for the objective function. But here the problem is minimization. So I need to go exactly the opposite direction to find the minimum value. That's why in this problem, as you see, I'm going to the left side. And when I go to the left side, the optimal value would be the point that I meet the last. So as you see, I go, go. I'm still inside the feasible region. I go further, and at point 0.3, I say goodbye to the feasible region. The last point that I see is the optimal point. Okay, so it's very easy to find. So it's very easy to draw it. First of all, you need to have practices to draw the feasible region according to the constraints. Then the next step is to find the direction of improvements. So these are these lines, these red lines, is the iso-cost lines. And to find, if I go into that direction, what is the last point I can see in the feasible region, which of course is an extreme point. And for this specific problem, it's points 0 and 3. So is it clear? So now, this is the solution to the part A question. It's saying that find the optimal solution of LP1 for this objective function, and if x1 is 0, x2 is 3, I can just put it in. For the objective function becomes minus 6, the objective function value. But The next question that comes to mind is that how much deviation from this direction if I have, I would get the same result. If I have if the direction was this, or this, or this, if you try with these directions, interestingly, you would get the same extreme points, the same objective value. So you can see there is a threshold for the objective function direction for which you would get the same objective value, but after some threshold, for example, if I go with this direction, the optimal point would be this one, not that one. So this is the area of interest, so that's why the cone of exit is introduced. The cone of exit, as you can see at the bottom of the page, the cone of directions that will take you away from the feasible region through this specific point is the cone of exit for that specific point. So why it's called cone? Because we are dealing with something like this, for example. This is a cone. Half an hour ago, we were talking about convex combination or convex sets. This is a cone. This is something different. How to define a cone? You need to know this in mathematics. That's how we define a cone. We say that if this is A1, this is A2, and I want to define this cone, I would say that this cone is lambda A1 plus mu A2 for lambda and mu non-negative. This set is the red spot that I already drew. This is a cone. This is a representation of a cone. And if the question is asking you what is the cone of exit, to find this specific extreme point as the objective optimal solution, you need to find vector A1, vector A2, and write the representation of a cone. The same is happening in here. Question part B is saying that show all the extreme points for feasible region. We already showed that what are the extreme points. Part C is saying that find the cone of exit at 0.03 for LP1. So this is a good exercise. We can do it together to see how we can find the cone of exit for one specific extreme point. It's very important, and you may encounter it in the quiz, so you need to pay attention. In order for 0.03 to be my optimal solution, the direction that I'm going to this point should be between the perpendicular line to constraint 2 and this constraint. All the points in between, all the directions in between would give me 0.03 as the optimal point. So how to represent this? How to find A1 and A2 vectors? I know that constraint 2, which is giving me this part, is minus x1 plus x2 less than or equal to 3. So what is the norm vector for this one? Since it's with less than or equal, the trick is you can say this is the coefficient of the first variable and the coefficient of the second variable. So -1 and 1 is A1. And the second line, the second direction, A2, is coming from the third constraint, which is x1 bigger than or equal to 0. I need to write it first with the less than or equal sign. So minus x1 is less than or equal to 0. So it becomes -1 and 0. -1 and 0. So this is the way I find the A1 and A2 vectors. Now that I have them, I can say the cone of exit for point 30 is -1, 1, lambda, -1, 0, mu, for lambda and mu bigger than or equal to 0. This is the cone of exit. Oh, sorry. This is the cone of exit for point 0 and 1, 0 and 3. But the fact is, this direction is for maximization. I'm improving this direction. Since LP1 is minimization, I need to multiply this by -1. If it's maximization, you need to report this one. If it's minimization, you need to report minus of this one. So for minimization, I would have 1 minus 1 lambda plus 1, 0 mu, and lambda and mu bigger than or equal to 0. This is how we find cone of exit for that specific point. So, is there any ambiguity for cone of exit definition? Why we are doing this? How we are doing this? Any questions? Okay. Part D is not specifying the word cone of exit, but the thing that it wants is the same as cone of exit idea. Part D is saying, for what range of values of C vector, which is the objective function direction, for problem LP2, point 0, 0 would be the unique optimal solution of LP1. And then it's saying that argue in terms of the cone of exit at this point, but without saying it, it's obvious that we need to use cone of exit because it's the same objective. We need to find for what ranges of the objective function I'm gonna get point 0 and 0 as the optimal value. So we can repeat this for point 0 and 0. Let's do this. For point 0 and 0, first I assume that it's a maximization problem. In order to get to these points, I need to be, let's draw perpendicular to this one, perpendicular to this one. I need to be in this direction between these two A1 and A2 vectors to have 0 and 0 as the objective, as the optimal points. So what is the first one? This is, again as before, -1, 0. The second one is 0, -1. And the cone of exit that I can introduce is -1, 0 lambda plus 0, -1 mu for lambda and mu bigger than or equal to 0. It's a maximization. The question is about LP1, which is a minimization. So then I multiply it by -1, and I say that the solution for minimization is this one. So for all the C's, for all the directions of the optimal objective function, which is inside this, I would get 0.0 and 0 as the optimal value. What is the example? For example, if lambda is 1, mu is 1, I would get 1, 1, meaning that x1 plus x2 as the objective function, if I have x1 plus x2 as the objective function, I would have 0.0 and 0 as the optimal value, optimal points. Any questions? As the last comment, in the solutions you have like explained version of what I'm saying here, so you can easily go over the details. But as the last comment, if they ask me not about the extreme points, if they say that when I can get this line as the optimal value, optimal points, when this line is the optimal points, the time that I go exactly the direction of objective function is exactly perpendicular to this line, that specific line would be the optimal points. We have alternative solutions in that case. Alternative solutions where 1 point of extreme point is involved, not 2 points, because alternative solutions may have different versions. Here we have just one extreme point and the rest goes to infinity. So how to find the cone of exit for this specific one? We say that if I go with this direction, I will end up with that specific alternative solutions. So what is this? As we discussed before, this is for constraint 2, so minus 1, 1. So I would show this with minus 1, 1 lambda for lambda bigger than 0. If C is inside this set, I would have that line noted with red color as my optimal solution. Is there any question? The trick is, I mean, you can count it. I mean, you can estimate it regarding the value of the vectors you already drawn. But the trick is you can easily, so as I told you, this line is minus x1 plus x2 less than or equal to 3. So minus 1 coming from this one, 1 is coming from this coefficient, minus 1, 1. But you should be careful. This should be less than or equal. If it's not less than or equal, change it to less than or equal and then use the coefficients. But again, when you come up with this one, you need to be careful. If it's minimization, you need to multiply it by minus 1 because minimization is the exact opposite direction of maximization. Any other questions? Okay, thank you very much. Good luck with the quiz.